Okay, so this is a quick video to try to help you with some of the concepts related to absolute and relative age dating. And by quick, I mean hopefully not more than 20 minutes, so we'll do our best. So what I think some people struggle with when we do absolute age dating is knowing where to start. So look, we try to keep it simple. The numbers can be very complex in real life, but the basic idea that we want you to get is that there are certain minerals, certain atoms that exist that are unstable. We call those radioactive, and they change over time from one atom or element into a more stable one. We can find some of those in certain minerals, and those can help us figure out how old some rocks are. Usually these are igneous rocks. And one of the most important rules is that when a rock forms and has a particular mineral that can accept this radioactive element, that in that structure there are no stable elements that are related to that. So the radioactive element we call the parent, and the stable element we call the daughter, or the daughter product, or the daughter element. The rule is that when that mineral is first crystallized from molten rock, and this is why igneous rocks are the ones we use to get age dates on, is that when those unstable or parent elements get locked into that mineral, there are no daughter products there. It hasn't decayed yet and hasn't had a time to get trapped in there. So they all crystallize and instantly they turn into a solid, boom, and I trapped all the radioactive ones. There's no daughter there. And then as time goes on, those atoms that are locked into that mineral slowly alter and they change from one element that's unstable to a more stable element. Okay, and so the one you probably have heard of is uranium into lead. So over time, certain uranium atoms that are unstable will decay, change, and turn into a lead atom. So we can use that idea to date some of these rocks because we've determined particular ratios and particular systems like a lead or a uranium lead take a certain amount of time, but for what we're calling a half-life, we can determine how long it takes for half of what you started with to decay into a more stable element, called a half-life. So it's a time that it takes for a certain amount, half of what you started with, to decay into a more stable element. And so what we want to say is, if we look at an example, we find our mineral that has these radioactive elements in it. And so let's say we find it today, we pick it up, we bring it back to the lab, we analyze it. And of course, these numbers are just made up, and the numbers would be very large and, maybe hard to work with. But for us, just want to get the concept, so these numbers work fine for us. We would argue these are the number of atoms that we counted from our little machine that could count the different atoms that we had in our sample. Now, if I look at this, it says there's 750 parent atoms, the unstable version, and 5,250 of the stable version, the daughter. Now, this rule up here, right, comes into play. I know that when this rock was first crystallized, this mineral here, right, it was in this igneous rock, a lava flow of some kind maybe. When that happened, everything that's in there had to be parent. There had to be no daughter product in there. So where did these 5,250 daughters come from? They came from unstable parent atoms that existed when the rock was first formed. So if that's true, then when I started out and our daughter amount was 0, that means this 5,250 plus the 750 that haven't decayed yet must have been the amount of unstable atoms that I had at the beginning when the rock and mineral first crystallized. So you always want to start like this. This should always be 0. And how do you know how many parents? Well, it's because you always add what decayed into the stable version, and with the remaining unstable version, you just add those together. So this is my starting point. What I want to first determine is how many half-lives have occurred in order to get the ratio that I see today. And so all I'm going to do is take this 6,000 and I'm going to take half of it. And so half of 6,000 is 3. What happened to my 3,000 unstable atoms? Well, they turned into something else. These daughter atoms that are now stable. And so this is a ratio that I would see if I collected a sample and one half-life had occurred, which means we took half of what we started with, okay? So we're going to need that information because every system, whether it's a uranium, lead, or a strontium, rubidium, whatever, type of decay, has a different half-life time. And so depending on what system we're using, maybe it takes 100 years to decay the half-life of a system. Well, that would mean in 100 years, this would be the ratio. Maybe it's 1,000 years. So if I use the 1,000-year, system, then this would take 1,000 years for one half-life to occur. But that's not how many half-lives have occurred to give me this ratio. So I need to keep going. Half of 3,000, what is that? Well, it's 1,500. So where did those 1,500 unstable parent atoms go? They turned into daughter. I already had 3,000 of them, so I just added 15, and now this is my new ratio. Does that match what I have here? It does not. So I haven't reached the number of half-lives that it takes to get this ratio, so I have to keep going. I've done one half-life and two half-lives, so I just keep going. Now I take my 1,500, half of that is another half-life. Now I have 750. Where'd that 750 go? Turned into daughter. I add it to my 45, and now I have this ratio. Does that match what I have? It does. And so now I know that it has taken 1, 2, 3 half-lives in order to get the ratio that I see today. Okay? And so you just keep going until you get the ratio that you see today. Of course, the numbers, we're making them work out nicely, and in the real world it could be, halves of, weird numbers. Don't worry about that. 3 half-lives have occurred. Now, I need to know what system I'm using so I can tell you how old my rock is. So if I tell you that the half-life of the system we're using is 200 million years, so for this particular unstable element, it takes 200 million years for half of it to decay. So what does that mean? Well, it took 200 million years to go from here to here, and another 200 to go from here to here, and another 200 to go from here to here. So what are we doing really? We're just multiplying the number of half-lives times the time it takes for half of this element to decay. So 3 times 200, 600 million. This process is the same no matter what these numbers are. These could be crazy numbers. This could be 1. This could be 58. This could be 1,000,000. This could be 20 million. We always take the two values and add them together so that this daughter is 0. And then I know my starting point. And then you're just going half, 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 half. Just keep going until you get back to this ratio. Count how many times you had to take half, and that's the number of half-lives. You have to be given the system's half-life. Like I said, if this system was 10 million, we would just be 3 times 10. It's 30 million. If this system was 1 billion, it'd be 3 times 1 billion, 3 billion. Okay? So this is the key, the starting point, knowing to start with 0 daughter and with the addition of whatever daughter you have today with the parent that still exists. And that ends up being the original amount of parent. Okay, so hopefully that helps with absolute age. If you're done and you know relative age, you don't need any more help, you can get rid of this video. But I'm going to talk just a little bit about relative age dating also. So a lot of times we give you these puzzles. We want you to put things in order relative to each other without knowing a number or an absolute age. So there's a couple really important rules that you follow in order to figure that out. And one of the most important is what's called superposition. It's the idea that sedimentary rocks, so these are the nice flat layered rocks, like think about the Grand Canyon, like a layer cake, right? Stacked on top of each other, or pancakes if you like. Putting pancakes on top of each other. When you see that, we'd argue that the oldest pancake is on the bottom and the youngest pancake is on the top. Because in order to get them in that order, I put down one, and then later on, I put another one on top of it. So that means that the one on the bottom was there first, making it the oldest, and then I keep stacking. And so we can tell an order based on a stack like that. Now there is a little tricky part, realizing that that stack can be tilted. We still want to say that the one that's on the bottom is the oldest, and then we could walk our way up. So if we look at this thing here, we think old on bottom. So, okay, old on bottom. Well, there's this big G thing here. It's on the bottom. Why isn't it the oldest? Because it's not a sedimentary rock. So the next rule that you have to remember is that igneous rocks were once molten. That's their definition, which means that they can go anywhere and do anything. They can ooze into any rock in any shape or form. And so as they're molten, they move into existing material and they melt some of the material they touch. But as they cool down, they also bake the edges and they bake rocks that existed, because I can't bake it if it didn't exist. And that's what these little reddish pinkish things are trying to indicate, what's called a baked zone. And so granite here is an igneous rock. I would tell you that if this was a quiz or a homework assignment. And so instead of saying, oh, G is the oldest, and then we just stack things on top, we would say, well, this thing must have oozed into stuff that already existed, and it must have baked those things. It is baking H. So H must have been there to be baked. It's baking B. B must have been there to be baked. Now this little stuff spilling over is just an artifact of PowerPoint. There's supposed to be no baked zone in D. And so here there's no bake zone. That means D didn't exist when this molten blob of granite oozed in. So my order would have to be that H was here first, then B, then this granite oozed in. Now there used to be other units above B, but they have been eroded away. I don't know what happened there, but I could still tell you that H was there, then B, then G, and then we go back to the stack. D must come next because it's this sedimentary rock. It's not igneous, because I would tell you if it was. And so then D, then E, and then we could say, oh, then A, C, F. That sounds pretty easy. And in this case, that would be a correct order. But we want to be aware of a couple things. If I asked you to put the fault in with that order, we would see that the fault does not cut A, C, or F. And that goes back to the bake zone story. You can't bake it if it wasn't there. You can't break it if it wasn't there. So the argument would be that all these things that we see an offset on, a stagger, means that they were broken and shifted. Usually faults are related to earthquakes. And so we would say the order would be H, B, G, D, E. Then the fault came along, broke everything that existed. Then later on there was some erosion, and then I stacked A, C, F. Okay? The final thing I'll just mention is that in this case, if I was giving you this as a homework or an assignment, I would also tell you that C is an igneous rock, which means it was once molten, and so as it was deposited, it actually baked anything that existed. Okay? Now, the granite is an igneous rock that oozes up inside the earth and never makes it to the surface. The C here is baking layer A. That tells us A was there, and then C must have come into contact with it. And that is true. It's also telling me that F did not exist, or it would have been baked. So the order of the last three is certainly A, C, F. Even though the bake zone is there, it doesn't change the order. Now, the tricky part is, sometimes you'll see a layer C where this is baked and this is baked. What does that mean? Well, the one baked means that it was probably a lava flow. It oozed up onto the surface of the earth. It flowed along the surface, like let's say a lava flow in Hawaii. There's no rocks above it, so there's nothing to bake, so it only bakes the stuff below it. But sometimes, like this big blobby oozy granite, you can get molten rock that oozes in between these flat layers and kind of flows along this, because this can be a weakness in the rock. it's exploited by the molten rock at depth, and it oozes in here. And it would bake the top and the bottom. But what does that mean for us? Well, it changes the order if we had a bake zone on the top and bottom. Because, just like I'm showing you here as it oozes in between E and D, they would have to be there in order to be baked. So if there was a bake zone on top here, that would suggest the order was A, then F. Then later on, some molten rock oozed up here and then decided to go horizontal and ooze between those two existing layers, baking both the top and the bottom. Okay, so those are some things to consider. So the three big things I would argue that you want to look for relative is superposition, stacking, when they're sedimentary rocks, old on the bottom, baked zones from igneous rocks, and then also what are called cross-cutting relationships. If it cuts across it, whatever's being cut had to be there in order to be cut. All right, so hopefully that's helpful, but as always, if you're still struggling or you need some more help, please reach out to me.